Hello class, today I'll be talking about an application of rotational motion, particularly rotational kinetic energy. So this is an example that you have studied earlier. It's the example of loop the loop. But you've studied the loop from the viewpoint of an object simply sliding down the loop. This time we'll be thinking about an object that's actually rolling down the loop. And it's rolling without slipping. Okay, so it's not slipping as it's rolling. If you have slipping and rolling at the same time, there'll be absolutely no connection between translation and rotation, and we cannot do this problem. It becomes impossible to do. So let's consider the basic setup here. You have a track. This track is popularly referred to as loop the loop because it's got this loop built into it. And the basic problem we have to solve is something like this. You have an object capable of rolling. Now it does not have to be anything special. It's just an object that's round in shape, that's capable of rolling. And rolls like that, goes up there and rolls down. So what we have to do is find out what the minimum speed or the minimum height needs to be so that the object is able to do the loop. So the right place to the right place to use for the potential energy of the object is its center of mass. So I'm going to take the center of mass of the object and call the height between the center of mass and the and the bottom of the track would be a good spot to consider as the zero of potential energy. So mind you, when the object comes down all the way here, it still has some potential energy because the radius of the object is going to not be zero. So we'll call the radius of the object little r, and it might make sense to call the radius of the loop then capital R. So we have to find the height at which I should release this object so that it makes this loop successfully and without falling down at the top. So let's just address that condition before we do anything further. That condition remains the same as before, so I'll just draw a little free body diagram here. You have the normal force acting down, you have the gravity little m times g, and then this object is also, let's see, it's going like this with some speed at the top, which I'll call v sub t. And don't forget that there's also a centripetal acceleration at the top, which I'll call a sub ct. And so Newton's law applied to the top part of the loop says that sum of all the forces in the negative r hat direction at the top must equal to mass times the centripetal acceleration at the top. So let's just analyze this. The normal force Fn, normal force at the top, Fnt, that's what it is, plus mg equals mvt squared divided by the radius. Now just be careful here. The radius is not r, but it's the radius as executed by the center of mass. So mv squared over that radius. So it's going to be capital R minus little r. That's the little trick there. If little r is close to 0, then of course it's the same centripetal acceleration as before, but you have to be careful there. Now when this goes almost to 0, that's when it barely makes the loop. So I cancel out the m's, and that gives me the speed squared at the top. It's just g times r minus r. Let's just save that condition and let's address the issue of what the minimum height must be. Let's call this the initial point I, and this is the final point F of our journey. So we have to apply the energy conservation between those 2 points for the next part of the analysis. Now, what to take for the nature of the object? What should it be? Let's take a look at our moment of inertia table on page 214 of the manual, and let's identify the objects that can actually roll. A ring can roll. So a ring is something like this. It can roll. A disc can roll. So I have here a 20-cent euro cent coin that can roll. And then 2 other objects can roll, and those are the solid cylinder and the hollow cylinder. So I've got here a huge ball bearing, which is a solid cylinder, and the hollow cylinder would be a hollowed out thing like a tennis ball, for example. So those 4 objects can roll, and look at what they have in common. They all look like mr squared times a number less than 1. For example, that's half, that's 2/5, that's 2/3, and that's 1. So 1 is like the biggest it gets. So rather than do a problem for a specific object, I'm just going to do it for all objects that can roll, and the 4 important things that we can think of are these 4 objects. So I'll call I equals C times mr squared, where C equals 1 would be your ring, C equals half would be the disk, C equals 2/5 would be the solid sphere, and C equals 2/3 would be the hollow sphere. So rather than commit to a C, we can do it for all the C's, and then and also remember that C equals 0 would be just a point mass. So that's just something that we need to also make a note of, because we want to recover the answers for the point mass. Now let's actually analyze the problem. We want to find the total energy here and set it equal to the total energy there. That's the principle of conservation of energy. Now, if it's rolling without slipping, it's not going to be losing any energy to friction because it's not sliding anywhere. So let us write the total mechanical energy equation. TMEI equals TMEF. The mechanical energy at the initial point is just purely potential energy, so it's just going to be little m times g times the initial height, h, and that's going to be equal to the potential plus the translational kinetic energy plus the rotational kinetic energy. The potential energy over here is mg times this height. So that height is 2 times capital R minus little r. Okay, so that's going to be mg2r minus r plus 1/2 little m vt squared. That's the translational kinetic energy, and the rotational kinetic energy is 1/2 I omega at the top squared. Now that unfortunately has got too many variables. We need to find h, and we do have vt squared there, but we don't have omega. Now, fortunately for us, there is a very nice prescription to find omega in terms of v, and that is the rotational translational connection. In an earlier video, I showed this connection here, and we've already used this a couple of times in later videos, but this is what it is. It's the translational speed is the radius little r times the rotational speed. Now, if this were not true, the object would be slipping, and there'd be absolutely no relationship between its rotational speed and its translational speed. In other words, it could stay in one place and spin its wheels. Well, that would be the case where it's slipping. We want rolling without slipping. So this is sometimes called the no-slip condition for that reason. So let's incorporate the no-slip condition in there and see what we get. So I'm going to have mgh equals mg times 2r minus little r plus 1/2 little m. For vt squared I'm going to, well actually wait, let me first substitute this. So 1/2 m vt squared plus 1/2, for I I'm going to substitute cmr squared. For omega I'll substitute v over r, so when I square omega I get vt squared over little r squared. Now observe this miracle, r squared cancels out, so the size of the object does not seem to matter here, although it does come into play over there, so it's not completely gone. Now I'll notice that vt squared here and a vt squared there, so I can possibly combine terms. So I'll get mgh equals mg 2r minus capital little r plus 1/2. That's cm, and that's just m, so it's going to be 1 plus c times m vt squared. At this point you notice that mass cancels out. Isn't that great? So the mass does not seem to matter at all. Now let's substitute for vt squared over there. So I get gh equals g times 2r minus little r plus 1/2 1 plus c g times r minus r. At this point you notice the planet does not matter either because gravity cancels out. And now we have the full-blown answer. The height that we need is going to be 2r minus little r plus 1/2 1 plus c r minus r. So that's the answer, and I don't offhand see a cuter way to write it. I mean, I guess you can take r and little r's and make two terms out of it, but it's not worth my time. So this is the answer. Now let's take some limiting cases. The first obvious the limiting case is that, let's see if we get the answers for the point mass. Let's take c equals 0, and if c equals 0, the object's not rolling. You can take little r equals 0 as well. There's nothing lost if you do that. So that limit, let's call this the first limit. It'll give me h equals 2r minus 0 plus 1/2 1 plus 0, which is just 1, r minus 0, which is just r, and that's 5/2 r. And that's a standard result. For a translational object, it's 5/2 or 2.5 times the radius of the loop. Now let's think of some interesting, let's still take the r to, the second limit we'll consider is still the limit this time when the radius of the object is much less than the radius of the loop. In that case, we can take the little r to be 0. Let's see what we get under that limit, under those conditions. So I'm going to get h equals 2r, because I'm neglecting the r there, plus 1/2 1 plus c times r. So this can actually be written more neatly. This is going to be r times 2 plus 1/2 is 2.5 or 5/2 plus c over 2. That's nice. This is the height of an object that's rolling down whose radius is much smaller than that of the loop. So that itself is a result probably worth boxing again. And even though that's the most general result, this is not a bad result to look at. So let's look at this result because it's easier to digest, and look at it for the ring and so on. So h of the ring is going to be r times 5/2, and the ring is c equals 1. It's 1/2. So that's like the I would say the worst case scenario, because that would be just want to make sure I did this right. Half plus r, yep, C over 2, yeah. So ring is C equals 1, and that's giving me 2.5 plus 0.5, which is 3R. So let's find out what it is for the disk. H disk. It's going to be R 5 halves plus C is now 1/2, so it's going to be 1/4. So it's whatever it is. And then you can do couple more things. H of a sphere, I'll just do the solid sphere. It's going to be R times 5 halves plus C over 2. C is 2/5. So if I do C over 2, I'm going to get 1/5. And that's again whatever it is. So the result that I'm fond of is 3R, because it's easy to remember. And 3 is certainly bigger than 2.5. So here you can see that the fact that the ring is rolling at the same time as it's translating, it means that you have to start at a higher point to make it go around the loop. All right, so that was an example of using kinetic energy to solve a real physics problem.